The purpose of this presentation is just to complete Objective 3.4, in which we've been talking about polar molecules and how that leads to intermolecular attractions and then interatomic attractions as well. And so last time we talked about how we can have polar bonds between things with great electronegativity differences, and we talked about how those polar bonds can lead to polar molecules if we reach a point where we have a molecule with no symmetry. And so if you look at the example below, we also want to look at what can happen to a collection of these molecules, both in the presence of and without an electric field. So without an electric field, these positive and negative ends of the molecule somewhat align themselves one to another for intermolecular attraction purposes, for electrostatics, kind of like you would see in ionic bonding, but not quite so strong, and then they just kind of line themselves up randomly making those connections. However, if we apply an electric field such that we give them a very strong positive center and a very strong negative center to align to, they will all shift their positions such that they make themselves orient in this field. So if we apply that field, all the negative sides will orient towards the positive plate, and all the positive sides orient towards the negative plate. And so this is just a property that these polar molecules have. If I place something nonpolar like CO2 inside the plates, nothing happens. I can apply all the electric field that I want, and they'll still just move around randomly without orienting themselves because they have no centers of positive or negative charge. The next little bit we want to talk about is how this polarity leads these molecules to then be attracted one to another. We call these attractions intermolecular forces because they're forces between molecules. The prefix ter or inter means one to another. And so we'll look at three main types of intermolecular forces. We'll talk about dispersion forces, dipole interactions, and hydrogen bonds. And something that you need to note is that both dispersion and dipole interactions are classified under the big umbrella of van der Waals forces, and these two are going to be weaker in comparison to the hydrogen bonds. So the first of these that we want to talk about is called dispersion. Dispersion is due to the motion of electrons. We know electrons don't sit still, they move in waveforms throughout the atoms, and when we make molecules, they move around inside the molecules. And essentially, this movement can cause a buildup of electrons on one side of the molecule or the other, at least temporarily. And so, whenever the electrons move all the way to one side of an atom, they kind of affect the electrons that are in nearby atoms. If they're all piled up on one end, then they push the electrons in the neighboring atoms away. And so they kind of cause those atoms to form temporary polarity as well. And so things we need to know about this is that it causes some polar attraction, but it's temporary and very weak. We also need to know that the number of electrons in a molecule or an atom will cause this attraction to be greater. The more electrons I have moving to one side or the other, piling up, then the greater the temporary polarity and the stronger that dispersion attraction will be. Now, it doesn't mean that it's as strong as some of the other IMFs we're going to talk about, but it will be stronger than, say, like hydrogen compared to iodine, for example. Hydrogen only has 2 electrons in its molecule moving around, whereas iodine has something like 106 that can move around inside those electrons or move around inside those atoms. And so the polarity of an iodine molecule through dispersion can be much greater than that for a hydrogen atom. Something else we need to know and make sure we know, this is a transient attraction, so it is the weakest of all intermolecular forces. Other things we discuss will be stronger than dispersion. We also need to note that dispersion can happen even in nonpolar molecules like H2. I mentioned that, but I want to make sure that you understand that dispersion is present even in things that aren't even molecules. Things like helium and xenon or noble gases will have dispersion forces. So they are very prevalent and present. All right, the other intermolecular forces that we have that fall under van der Waals would be our dipole interactions. These occur in our permanently polar molecules, things like HF or HCl. They're a weak attraction for partially positive and negative regions of molecules, but they are stronger than dispersion forces. This largely has to do with the fact that they're permanent. and the fact that the electrons are more separated, so we have some more definite poles. So this would be the same kind of attraction we would see between cations and anions in ionic systems, only to a much lesser degree because the charges aren't full, they're just partial. Moving beyond van der Waals forces. Oh, sorry, here's the picture of dipole interactions. I forgot I had that in here. So the yellow parts of the molecule are negative and the green parts are positive. If we look through here, we see negatives and positives connecting with many different molecules all around to build this web of attraction that starts to hold the molecule together. And again, it's stronger than the previous dispersion force because it stays. It's not moving. These charges are permanent, and so the connections that they make can last a lot longer. All right, moving beyond van der Waals forces, we move into hydrogen bonding. And what hydrogen bonding is it's the attraction of a hydrogen atom that is covalently bonded to a highly electronegative atom. This would be nitrogen, oxygen, or fluorine that we consider to be highly electronegative. And so it's the attraction of a hydrogen connected to one of those for the unshared electron pairs of a highly electronegative atom. It can be in the same molecule or a different molecule, but it just has to be a highly electronegative. Now, the reason that this works is because hydrogen has no shielding on its first electron level. That's the only level it has. There's no underlying electrons. And so when it connects to a highly electronegative atom, that highly electronegative atom draws that electron away from the hydrogen and essentially leaves behind a pure bare positive charge. Now it's not totally positive because the electrons do move back there every once in a while since we're talking about covalent bonding, but it's far more positive than what we see in normal dipole interactions. And so because it will become very positive, and then if another electronegative atom that has maybe unshared pairs of electrons will have a very concentrated negative charge, and so the attraction between those is kind of like a dipole interaction on steroids. It's just a very positive and very negative attraction. So this is the strongest of our intermolecular forces, and in fact it's so strong that it accounts for about 5% of the strength of a normal covalent bond. And so if I wanted to rank these from weakest to strongest, we would start with dispersion being the weakest, then transition into dipole interactions, and finally hydrogen bonding being the strongest of all these attractions that we've mentioned. And so here's kind of what hydrogen bonding looks like. If we look at this molecule picture they're showing me down here, the red balls represent the oxygen atom in a water molecule, and the blue parts represent the hydrogen atoms in the water molecule. So the oxygen parts, the red parts, should be somewhat negative, and the blue part should be somewhat positive, and so they will attract each other. So that the positives, the hydrogens of one water molecule, attract to the oxygen of another, while its hydrogens attract to the oxygen molecule of the outlying molecules of water, and this will happen over and over and over again and help bind water together. All right, the last little bit that we want to talk about here is our interatomic forces. And specifically, we want to talk about metallic bonding and how it's similar and different from covalent bonding. So when we're talking about interatomic attraction, what we mean is attraction between atoms. Just like intermolecular meant between molecules, interatomic means between atoms. And so what we have for metallic bonding then is the attraction of free-floating valence electrons from metal cations. Essentially, when metals get together and form a nice little crystal structure of metal atoms, they do something that other things we've talked about don't do. Essentially, all those atoms just release their valence electrons into a pool, which we're going to refer to as an electron sea. And when they do that, they leave behind little metal cation centers. And it's the attraction of these little metal cation centers for that giant sea of free-floating valence electrons that help hold metal atoms together in crystal structures. Whereas when we took metals and nonmetals and put them together, we had to do a transfer of electrons to get that to happen. And so really that's how we model metal structures. We model them as a nice little sea of mobile valence electrons flowing around a set of metal cations. As you can see in the picture down here, this is our standard ionic bonding that we've talked about before, where we have repeating patterns of fully positive and fully negative ions in a crystal. Whereas in our free-floating model for metals, we have a bunch of positives, which happen to be are metal cations, and then all these valence electrons that they happen to have dropped out into the sea. So how can we explain some properties of metals using this model? Well, one thing we know about metals is that they conduct electricity. So if we look over here and think of these electrons as really free floating and able to move, kind of like water, then we could imagine hooking a battery up to a piece of metal. And what a battery does is essentially pump electrons into one side and pull electrons out of the other. Now in an ionic crystal, this doesn't go. These are locked into a crystal pattern. The negatives are not electrons, they're actually negative ions that are highly attracted to the positives around them, and they're not mobile. If you remember, to get ionics to conduct electricity, we had to melt them or dissolve them in water to break their attraction so that they would be mobile. However, we're saying in a metal that these electrons are very mobile. So if I hook a battery up to a piece of metal, I can push an electron in one side and have an electron jump out the other side, and it's no big deal to the metal. It doesn't care as long as it has the right number of electrons. They're mobile, they're flowing in and out. It really doesn't care. So that will allow it then to complete a circuit because electrons can move into it, through it, and out of it. Over here, in able to move in, through, and out, we have to break the attractions. Finally, we want to discuss how this helps us understand the malleability and ductility of metals, so their ability to be hammered into thin sheets and worked into shapes, and also their ability to be drawn into wires. Essentially, over here with a crystal, for a salt, when we try to do this, if we try to hammer on a salt or we try to draw a salt through a nice hole to make a wire, we push those positives and negatives close together. And when they form their crystal lattice here to form their salt crystal, they're as close as they want to be. So when we try to hammer them or pull them through and push them close together, they push back very hard with their strong repulsions, and essentially they shatter the crystal. However, in a metal, we can do this. We can hammer it, we can push it through a hole because these electrons are very, very small and mobile. And so they're able to move in, out, and around these positive cations and insulate them from each other. So when they touch each other, as long as they're both touching an electron, they don't repel each other. That electron provides them almost like a grease, if you want an analogy. It would be like having ball bearings that have been dipped in grease. They just roll right over each other. And so this allows them to move close together over and around each other so that we can work them into shapes or draw them into wires.